Definition of magnetic flux density. Magnetic flux density is the force experienced by a conductor of unit length placed perpendicular to the magnetic field and carrying a current of 1 ampere. And the unit of magnetic flux density is your Tesla, and that is its base units. Let's take a look at Fleming's left-hand rule and how the direction of the magnetic force can be determined when a current flows through a magnetic field. Let's run through the experimental setup. In this experimental setup, you have a magnet that provides the magnetic field. You have a battery that provides the current that is flowing in this direction. We have a magnet where the magnetic field lines flow from north to south. So that is the direction of your magnetic field. Finally, by using your left-hand rule, you find that the force acting on the wire will be acted upon in this direction from left to right. In this kicking wire experiment, it is observed that when the current increases, the force acting on the wire increases proportionally as well. In the same vein, when the length of the wire that is exposed to the magnetic field increases, the force acting on it increases proportionally as well. Finally, it is also determined the magnetic force acting on the wire is directly proportional to the magnetic flux density. So with that, the formula is F equal to BIL, where L is the length of the wire, I is the current flowing in the wire, B is the magnetic flux density, where the magnetic field line is perpendicular to the direction of the current flow. And using Fleming's left-hand rule, we will know that the direction of the magnetic force is acted upwards in this example. Let's take a look at another example. Say, assuming the current is flowing in this direction, while the direction of the magnetic field is at an angle theta to the direction of the flow of the current. In this case, we could resolve this magnetic field in two directions. Since magnetic field lines are vectors, we can resolve them into Bx, where the magnetic field line is directly perpendicular to the current, and we can resolve another component By, which is parallel. Since By is in the same direction as the current, it will not give rise to a magnetic force. And hence, when deploying the formula F equal to BIL, we have to note that B has to be perpendicular to the force F. And in this example that is given, you will find that F will now be equal to BXIL. And Bx is equal to B sine theta. Hence, because of that, we'll end up with the expression of F equal to BIL sine theta.